Hello students, welcome to my YouTube channel Integrated Physics Studies IPS. एथरे मु ऑलरेडी प्लस 2 सेकंड ईयर सिलेबस कंप्लीट कर सारछि एबे मु प्लस 3 सीबीसीएस ऑनलाइन क्लासेस रो वीडियोज गुडा अपलोड करिवि जदि भल लागिला ताले लाइक कर देबो एवं सब्सक्राइब कर देबो जो वीडियोज गुडा मु अपलोड करिवि तार नोटिफिकेशन पई एठी बेल आइकन को ऑल रे सेट कर देबो गोटे इंपोर्टेंट जिंस वीडियोज रो ऊपर एठी जो 3 डॉट्स देखुछो तार क्वालिटी एठी देखो बाय डिफॉल्ट 360 अछि तमे ताकू पढे मध्ये परिबो एठी एडवांस रे क्लिक करी तमे रिजोल्यूशन बढ़े परिबो प्रति वीडियोज रे मु पीडीएफ लिंक देबी ताकू एठी ड्रॉप डाउन लिस्ट रो तमे क्लिक करी डाउनलोड मध्ये करि परिबो पीडीएफ को लास्ट रे एठी जो मोर चैनल नेम अछि याकू क्लिक करी तमे एठी प्ले लिस्ट को जाई मु प्रति वीडियोज को यूनिट वाइज एज पर सिलेबस सजाई की रखिथिबी तमे सर्च करि परिबो ओके थैंक यू हेलो स्टूडेंट्स आज रो टॉपिक रे हमें साइज इफेक्ट्स इन नानो सिस्टम ए विषय रे पढिबा already in the beginning where we have read about the nanoscale system, its introduction. So we have seen that whenever we are making the things smaller, then we are getting more advantages, right? So in the modern semiconductor industry, miniaturization, that means making the things smaller. So when we make the devices smaller, then it delivers more efficient performance, or it enhance the performance of that device, right? Now the main question is, what would be the limits of this miniaturization? Theoretically, if we see, the devices can be miniaturized up to your atomic level. So here the sizes vary from some fractions of nanometer to few hundreds of nanometers, right? Now nanotechnology deals with all these kinds of human designs, that is your artificial working devices, and these are produced in a controlled and reproducible manner. Okay, so the idea of this miniaturization of the size scale is interesting due to the fact that the size approaches the atomic scale, and the relevant physics which is associated with the system now changes from classical domain is applicable when the size is macroscopic. Okay, now when the size reaches or approaches to the atomic scale, that is your nanoscale, then we are coming to the quantum mechanical regime. Okay, so these changes in the behavior from classical to atomic scale via mesoscopic domain can be explained by modern quantum mechanical treatments, right? So it must be noted that these changes from classical physics to quantum mechanical nanophysics, and it may mean that some of the existing devices will fail, while the same changes can open up the possibilities for new devices, right? Suppose for example, in the past few decades, if you consider the landline telephone system, it was replaced with a keypad mobile phone system which you can carry from one place to another. Now the keypad phone was replaced with a smartphone. Okay, so apart from dialing a number, a smartphone has various applications. Okay, so you can also take the example of your computer system, then your television system, which were in form of bigger size boxes. Okay, and now the size is becoming smaller and the performance is increasing. Okay, so if we consider now the size of various objects, natural and artificial, then starting from human hair to DNA structure, all these are natural objects. Okay, so the nature evolves itself from micro scale to nanoscale structure. Okay, similarly we can see the modern world is now shifting its attention from micro devices to nano materials, that means the nano devices, right? So the broad spectrum of micro and nano regime is shown in the following figure. The left side is your natural occurring substances or materials, and the right side we have the artificial materials. So first, your natural materials, we have the legs of an ant which is varying from 1 to 2 millimeter. Then human hair, okay, it is having a size of 10 to 50 micrometer. Thereafter the red blood cells, which is having size of 2 to 5 micrometer. Then poliovirus, okay, it is having a size of 20 to 30 nanometer. Okay, so now the nano world is coming. Okay, now next one is your DNA, deoxyribonucleic acid. Its size is zero point 0.5 to 2 nanometer. Okay, these are the natural substances. Now the artificial substances, first one is your head of a pin. Okay, this is a safety pin. Its size is zero point 0.5 to 1 millimeter. Then MEMS, micro electromechanical system. Okay, MEMS devices having size varying from 10 to 100 micrometer. So these are lying in the micro world. Thereafter your visible spectrum বা দৃশ্যমান বর্ণালী जो light ର. Okay, then your nano world. Nano world, and it has your quantum coral which is about 10 to 20 nanometer in size, and we have the CNT, carbon nanotube, which is about 2 to 5 nanometer in size. Okay, so these are some of the examples, the descriptions of your nano and micro regime materials. Okay, now let us have some of the examples to understand the size effects of your nano systems. First one is the response time, which is increasing for a miniaturized, that is a small, very small, teeny, simple pendulum. Okay, now we know that the resonant frequency of a simple pendulum, it is given by nu equal to 1 by 2 pi into square root of g by l. Okay, now here g is the acceleration due to gravity, l হয়ে গেল এটি length of the simple pendulum. Okay, and it shows that the simple pendulum, suppose we take having a length of 1 micrometer, then it will generate a frequency of about 1000 hertz, right, corresponding to the time period of 1 millisecond. Hence, if we make the simple pendulum smaller in size, then this miniature version will have a much faster response time with respect to the normal simple pendulum, which would have a resolution of 1 second if the pendulum length is 1 meter. Okay, another example, we can see the thermal time constant, which is decreasing in case of your smaller system. So for this, let us consider a hot body which is maintained at a temperature greater than 0 Kelvin, and heat capacity per unit volume is capital C. Now this is connected to a cold body via a heat channel, okay, having a length L and area of cross section small a. Okay, so obviously heat will flow from hot body to cold body through this heat channel, and it is having a heat capacity capital K. Then the rate of flow of heat from hot body to cold body will be given by dq by dt equal to kat by L. Okay, suppose this is equation 1. Now at steady state, this rate of flow of heat must be equal to the rate of loss of heat from the hot body. So dq by dt must be equal to minus cv dt by d small t. Okay, and here V is the volume of the hot body, and here we have applied a negative sign because it is indicating that heat is being lost from the hot body, right? Now you can equate equation 1 and 2 so that kat by L equal to minus Cv dt by dt. From this we can calculate the value dt by t equal to this much, and let us take this cvl by ka to be equal to tau. Okay, here tau is the thermal time constant, okay, which has the dimension of length square under isotropic environment. So using equation 3, we get dt by t equal to minus 1 by tau dt. Now integrating both sides, having temperature limits from T0 to T and time limits from 0 to T, and finally we are getting the result. The temperature T is equal to T0 exponential of minus small t by tau. Now from equation 4 we have got tau equal to CVL by Ka. So clearly this thermal time constant tau strongly decreases with a decrease in the size of the system. right? So this phenomenon is used for data storage system, okay, where the data bits are recorded with a resistively heated AFM tip. Okay, AFM means atomic force microscope. Okay, and they are detected by integrated piezoelectric sensor, PZT. Okay, here PZT means PBZRTIO. Okay, so this is lead zirconate titanate. Okay, here we put ZRX and Ti1 minus X, then O3, right? So PBZRX, Ti1 minus X and O3, this is your PZT or lead zirconate titanate. Okay, this is a piezoelectric sensor. Okay, and this system consumes less power and its response is much faster, right? So the image of AFM tip and its working principle are shown in the following figure. Okay, the left side figure is the, this is the tip of AFM, that is your atomic force microscope. Okay, it is the tip, right? And its radius is measured about 0.18 micrometer. Okay, this is the image as got by SEM, the scanning electron microscope image. Okay, and the right side figure is the schematic diagram of working principle of AFM. Okay, as you can see, the light coming from this laser diode is incident on this portion of the cantilever spring. Now the AFM tip is connected to this sample so that we can detect its properties by means of this sensitive photo detector, right? Another example is the disappearance of friction in case of highly symmetric molecular system. Now, according to scientist Eric Drexler, the viscous and frictional forces are assumed to be zero or absent in case of molecular scale systems. Theoretical model jodi dekhiba, it shows that the self alignment of nanometer scale wheels and axles in vacuum will lead to absolute zero space for any fluid in the interface between the surfaces. Okay, so kiछि भी fluid रहिबा पई जागा आउ रहिबो नहीं. Hence, these moving parts will no longer experience any fluid viscous forces between them. But however, these moving parts may encounter some frictional forces, if any, okay, but it will be negligible at a much lower level than the ordinary mechanical frictional forces in these macroscopic moving parts. Suppose we take an example in case of your nested carbon nanotubes, okay, nested CNT, which are rolled sheets of graphite as shown in figure. Okay, so this is shown in this figure. The right side we have the nested carbon nanotube, which is obtained from the rolled sheets of graphite. Now in the left side we have the single graphite sheets in cylindrical shape. Now if we add some more graphite sheets in coaxial way, then we get the multi-wall nanotubes, and on continuing this process we get finally the nested carbon nanotube, which is having no dangling bonds perpendicular to their surfaces. Here dangling bonds means an unsatisfied valence on an immobilized atom, right? And the second thing is that there are no molecules between the surfaces of two adjacent tubes because they are so closely rolled. Okay, hence the medium between the very closely spaced moving parts is nothing but your vacuum. Therefore the motion between two neighboring carbon nanotubes is almost frictionless, so friction is absent or you can say negligible, right? Finally, the molecular bearing of biological rotary motors, okay, is an other example of your frictionless motion. Now in case of your biological rotary motors, the molecular bearing, okay, like that of your ball bearing in case of your cycle. So here the molecular bearing rotates flagella to move cells in the liquid, right? So this flagellum, it is something like your lubricant. Okay, it is attached to the shaft and it rotates freely in a molecular structure. Okay, the rotation thereafter transmits the torque and power, and the motor operates continuously over the life of the cell, which suggests a frictionless molecular bearing. As shown in this figure, it is the schematic representation of E. coli bacteria flagella rotary motor. Okay, so this is the schematic figure, and its size is nearly about 27 nanometer. Okay, so this is the rotor, and this is the stator, then the inner membrane, outer membrane, then the bushing. Okay, like that of your uh, machines. Okay, machine रे जेमती bush गुड़ा लगी था से बड़े एठी हमें देखुछु. This is the universal point, and then the flagellar filament. Okay, you can see this filament is rotating, right? And this rotation is up to 100,000 rpm, that is 1 lakh rotations per minute, right? तापरे देखो ए क्वांटम साइज इफेक्ट्स बा साइज इफेक्ट्स ऑफ नानो सिस्टम आ गोटे बहिरु मु नेइछि. ओके, सो एठी भी सेही जो साइज इफेक्ट को लेंथ स्केल सहित ये रिलेट कला. ओके, एंड दिस प्रॉपर्टी ऑफ मटेरियल actually it is characterized by the specific length scale. ओके, जोटा आमे आगु पढ़ीचु जेतेबेले आमे नानोमीटर डायमेंशन रे पहुंची जाउछु. गोटे बल्क मटेरियल अछि, so that we decrease its size and reach up to nano dimension, right? So if the physical size of the material is reduced below this length scale, then its properties change and become sensitive to the size and shape. Okay, so the relevant physical length scales are actually relative to the natural electron or hole length scales in the parent bulk material, and these are either your de Broglie wavelength of electron or hole or your exciton Bohr radius, right? तापरे ये जो नानो मटेरियल रो जो साइज इफेक्ट को ये देखौची, जोटा कि गोटे यार फैक्टर ये देखेला most important size effect is your increase in the surface to volume, that is S by V ratio for the nanomaterials over the bulk. And this is because in nano sized system up to 50% atoms lie at the surface of a nanostructure, and this makes the nanomaterials more chemically reactive. Okay, and the surface is therefore potentially important in dictating the material's optical and electrical properties when the nanometer size has been reached. Okay, for this it has taken the example of a semiconductor, gallium arsenic semiconductor, and it has described. Okay, thereafter another your size effect is important one is your dependence of resistivity of a material on the scattering processes, right? As we know, the average distance traveled by a charge carrier without undergoing any scattering is called its mean free path, that is L equal to V tau. Here V is the drift velocity and tau is the time interval between two consecutive scattering events of the charge carrier. Now in case of metal, the mean free path is lying in the range 2 to 50 nanometer, and pure samples of metals having longer mean free paths as there is less scattering due to the lesser number of scattering centers. Now the resistivity of a polycrystalline conductor or semiconductor, which is composed of microcrystallites with diameters significantly greater than L, resembles that of a network of interconnected resistors. But however, when the microcrystallites dimension becomes comparable to this length L, then the resistivity depends mainly on the scattering from the boundaries between the crystallites, because the scattering or collision may be occur between the charge carriers, otherwise they may be scattered from the boundaries of the crystallites. Now various types of defects in the lattice will limit the mean free path of the charge carriers and can bring about the scattering of the electrons, and hence it will limit the electrical conductivity. So this occurs however only when the defect size is comparable with the size of the charge carriers, right? Finally, another size effect ଏଠି କହୁଛି due to the level of doping. Doping means we know that Suppose for the case of your intrinsic semiconductor, by means of doping, that is by adding some impurities, maybe that is trivalent or pentavalent, we can increase its performance or efficiency. So if we add the trivalent impurity like your boron, then it will be a p-type semiconductor. Okay, and if we add a pentavalent impurity like that of your phosphorus, then it will be a n-type semiconductor. So the intrinsic semiconductor after doping will become an extrinsic semiconductor. So the level of doping is nothing but the carrier concentration in a semiconductor. So quantum structures such as your quantum wells, wires and dots are characterized with very small concentration of electrons, which are your carrier charges. So a higher doping level is required to have any significant electron concentration if size of the nanostructure is reduced below the electron de Broglie wavelength. So this is all about the size effects in the nano systems. Thank you.